Suppose that we are given a function f, data generating function f on a data space X. Find and suppose that DNN is parameterized by parameter gamma, and find the unknown parameter gamma of DNN so that the network is equal to function f. So f is given and gamma is unknown. So this is really abstract because I do not specify any structure, network structure of DNN. But uh, as long as we luckily find the solution operator to this gamma, we call it the Ridgelet transform. So the Ridgelet transform is like if we substitute the Ridgelet transform of f to the place of unknown parameter distribution gamma, then DNN of gamma equals f. It solves this learning equation. We can regard this learning equation as the strict version of a learning problem. Learning problem typically minimizes the square loss between training data on the training data set. So we can regard this as a learning problem as a variational problem, but this is equation. So equation is much a harder version of a variational problem. But anyway, we can find the rigid transform. So that's why I I consider this a hard problem. And traditionally or originally, the rigid transform is known for depth 2 fully connected neural network on Euclidean space case. So in the first half of this talk, I will explain this traditional or classical rigid transform for depth 2 case. And in the second half, I will explain the depth n case. I mean, deep n case, deep neural network case. So because this is a recent discovery. Okay. So let's start. Let's start the first half. So as you may know, uh, uh, but I will introduce a shallow neural network. So shallow neural network is a function of X with the parameter A and B and C. And here sigma can also be a parameter, but we typically we fix sigma. Sigma is typically a hyperbolic tangent, or Gaussian, or ReLU. Anyway, those are fixed. So during the training process, we adjust those A and B and C. Okay, and in order to visually understand the shallow neural network, here I plot the figure of a two-dimensional input case with a single hidden unit. So in this case, here the bottom two-dimension space corresponds to the input space, and the vertical axis corresponds to output dimension. And for the purpose of visualization, I choose sigma to be a Gaussian. So you can now see the Gaussian shape in this section. And you can also see this constant direction, but this constant direction is controlled by the weight parameter A, right? Because if X is orthogonal to A, then it doesn't have any effect on the output, right? So in the visualization, it is visualized as a constant direction, and we call it reach. So this is the origin of the Ridgelet transform. And this B controls the location of this ridge function. So if we change this B, the ridge will be parallel transported. And this C controls the height of this ridge. Okay. So for this shallow neural network case, we can geometrically understand the role of parameters A and B and C. Okay. And before stepping into the mathematical explanation, I want to explain intuitive understanding how neural network approximate functions. So on the left panel, you can see the face of Christ, and this is made of pins and threads. So, and this is made by an Italian artist, Petros Brelis. And so if you align many segments or threads on this two-dimensional space, then you can make cross points. And if you gather cross point, you can make a darker area, right? And on the other hand, if you avoid making cross points, you can make a brighter area, right? And by controlling the density of cross points, you can make an arbitrary two-dimensional signal. This is an intuitive understanding of how a neural network approximate a two-dimensional signal. What do you mean? What do you mean? Because in the previous slide, I explained the neural network, shallow neural network is a linear combination of ridge functions. And for two-dimensional case, this single hidden unit corresponds to a single ridge function, single ridge on two-dimensional space. And shallow neural network is a weighted sum of ridge functions. So they align many ridges on two-dimensional space. So by controlling the location and direction, so direction A and location B and the height C of ridges, neural network can approximate an arbitrary two-dimensional signal. This is a mechanism. And this mechanism is not unique to a shallow neural network, but this is also employed by other methods such as Fourier series expansion. Fourier series expansion is a linear sum of plane waves, right? And by controlling the direction and location of plane waves, you can approximate an arbitrary two-dimensional signal. And a similar mechanism is also employed by X-ray tomography. On the other hand, you can draw illustrations by putting many points, not lines. For example, pixel art or this computer screen employs the drawing by points. And as a machine learning method, corner regression corresponds to this drawing method by points. So in this sense, the corner method and the neural networks are a bit different as a function approximator. Okay, this is an intuitive understanding of how neural network approximate function. And for two-dimensional case, maybe we can manually compute which A and B and C to use according to this scheme. But for high-dimensional case, it's really hard to find which A and B to C, which A and B and C. And the Ridgelet transform, the main topic of today, automatically compute which A and B to use by in the form of integral transform of function f to be approximated by neural network. Okay, to introduce the Ridgelet transform, I first introduce integral representation of neural network. So the upper panel corresponds to the ordinary finite width neural network. That's what I already explained. So even a single hidden layer case, the analysis of parameter is already difficult. In particular, because those hidden parameters A and B are inside a nonlinear function sigma. That makes everything complicated. For example, if we twice A the function will not be twice. This is a nonlinearity, right? So still, even a single hidden layer case, the analysis is difficult. So the bottom panel corresponds to infinite width. And this is a mathematical trick to linearize the nonlinear parameter of neural network. How? So the integral representation. So let me explain the integral representation of neural network. The integral representation of neural network is an infinite sum of basis function of a neural network. And in this integral representation, all possible hidden parameter A and B are integrated. So we do not need to choose which AI and BI to use. Instead, by waiting on them, we indirectly choose which A and B to use. And this gamma, this weighting function gamma, is in the place of a linear parameter. This is originally, it corresponds to CI. So even in a finite neural network case, CI is a linear parameter. I mean, if we twice CI, then the network will be twice, right? So, and in the infinite neural network case, if we twice this weighting function gamma, then the function itself will be twice. And if we suppose we have two weighting functions like a gamma 1 plus gamma 2, if we substitute gamma 1 plus gamma 2, then the function S of gamma will be summed, like a S of gamma 1 plus S of gamma 2. Okay, so this is a linearization trick of a neural network. And in addition, it depends on the choice of the class of gamma. But if we allow gamma to be a large to be an element of a large class of distributions, then we can simply put gamma to be a finite sum of Dirac delta. Then we can exactly reproduce a finite neural network case. Okay, in this sense, the infinite wide or integral representation of neural network is an extension of a finite with neural network. Okay, so this is an explanation of integral representation, and the Ridgelet transform is an inverse transform for the integral representation. What does it mean? So first, the definition of Ridgelet transform is given in this box. Given an arbitrary function on Rm and an arbitrary function rho, this rho could be different from activation function sigma. And the Ridgelet transform is defined as a scalar product, scalar functional product of function f to be approximated by neural network, and rho a dot x minus b with respect to data variable x. So it's essentially measures the similarity between fx and rho a dot x minus b. Okay, this is the meaning of a Ridgelet transform. And suppose that the sigma activation function sigma is a temporal distribution. Temporal distribution is for example, hyperbolic tangent or ReLU or Gaussian. Almost every possible choice of activation function is a temporal distribution. On the other hand, suppose that the rho is a Schwartz test function, or it is sometimes called a rapidly decreasing smooth function, like a Gaussian. And suppose that f is an arbitrary square integrable function, then if we substitute the Ridgelet transform of f to the place of unknown function gamma, unknown weighting function gamma of a continuous neural network, then continuous neural network operator reproduces the original function f up to the constant depending only on sigma and rho. So this double parenthesis is bilinear form of sigma and rho, but this is independent of function f, so it's a constant. And this reconstruction formula have two meanings. The first meaning is that because S of gamma is the mathematical model of continuous neural network, and the choice of function f is an arbitrary square integral function, this reconstruction formula means that the continuous neural network can approximate an arbitrary square integrable function. This is the first meaning. And the second meaning is that the Ridgelet transform R and the continuous neural network operator S plays the same role as the Fourier and the inverse Fourier transforms. So, the Ridgelet transform encode the information of function f on the parameter domain, right? On the other hand, the Fourier transform encodes the information of function f on the frequency domain. On the other hand, the Fourier inverse operator synthesizes or reproduces the original function f, right? Similarly, the continuous neural network operator synthesizes or reproduces the original function f. Okay, so f and f inverse plays the same roles as R and S. Okay, that's the second meaning. Okay, so and I have several numerical experiments. This is a one-dimension signal case for the purpose of visual understanding of how Ridgelet transform looks like. So as a one-dimension signal, I employed a truncated sinusoidal curve, and then and this is a figure of a truncated sinusoidal curve, and this R of f. We can compute the Ridgelet transform R of f by using a numerical integration technique at every fixed A and B. Then we obtain a two-dimension signal because we have one dimension A and one dimension B. And typically the image of a Ridgelet transform is oscillated because the choice of Ridgelet function is typically oscillated, and now the function itself is also oscillated. And,
Excuse me.
yes?
Excuse me. If we choose this rho equals to the activation function sigma,
yeah.
then this is a bit like a tight frame, right?
Oh, yeah. We can choose the rho to be activation function sigma.
Yeah.
Yes, we can choose. But in this case, the image will be less oscillated.
Okay.
Yeah, in order to now, the choice of a sigma and the rho is somewhat asymmetry. Sigma could be a temporal distribution like Gaussian or ReLU or hyperbolic tangent, but the rho should be more regularized functions like Gaussian.
Okay.
Yeah, these pairs in some sense are dual. S
Oh, okay.
and S corresponds to dual to each other. Yes. Yeah, technically we can choose rho to be sigma. Yeah, thank you. Thank you for question. And if we change if we use a different rho, we of course obtain a different transformation pattern. These four are slightly different. For example, in the leftmost case, you can see 8 hands. I mean, yeah. But on the rightmost case, we can see, I guess, 1, 2, 3, 4, 5, 6, 7, yeah, 14 arms. And only when the coupling conditions sigma and rho are not orthogonal, we can reconstruct the original function, like rho 2 and rho 4 case. Here, rho k is a Hilbert transform of of a kth derivative of Gaussian, rho 0. And we can analytically verify that rho 1 and rho 3 are orthogonal to hyperbolic tangent, but rho 2 and rho 4 are not orthogonal. So for orthogonal case, of course, all the information of original function f is encoded on the parameter domain, but the reconstruction result degenerates to zero function. This means that the neural network does have a non-trivial null element. Okay. And I prepared another numerical example. So consider training a finite width neural network with a hyperbolic tangent activation function by using SGD. And the data set is again the same as a truncated sinusoidal curve. And here I assume that the finite width network has 10 hidden units. So, and after running a gradient descent, after the learning process converges, we obtain 10 ABC points, right? This is a three-dimensional space. A and B and C is shown in color. So because we have 10 hidden units, we will have 10 pairs of ABC. And now we have 10 points in this ABC space. I mean 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points, right? And if we change the initial parameter, because the learning process is non-convex, they converge to different points. So if we train two networks, we typically the converged points will be different, and we can now see the 20 points here. So if we train 5 networks, then after learning process, we will obtain 50 points on this ABC space. So, and by increasing the network, then gradually the pattern emerges. And so after training 1,000 network, we obtain 10,000 points on this ABC space. And obviously there is red arms and blue arms. So blue means that network has a negative intensity, and red means that positive intensity. I mean the coefficient C is positive, and the blue means that the C is negative, right? And the green is just a 0. So this means that the hidden unit is not used. And we can mathematically show that this unique distribution of learned parameters by gradient descent converge to the Ridgelet transform. For example, you can see a red arm in the left panel, right? And almost, so those red points accumulates around the red arm in the Ridgelet transform. So, and in this sense, understanding the parameter of neural network is transformed to understanding the Ridgelet transform of a function f. And what I want to say here is that the neural network parameter is considered to be a black box, sort of a black box. But if you know the Ridgelet transform, it's not much like a black box because it's just an integral transformation of original function f, right? So that's a motivation to investigate the Ridgelet transform. Okay. So this is a first half of the Ridgelet transform. So I explained to this moment, I explained the classical Ridgelet transform for depth 2 neural network case. But now in the deep learning age, there are a variety of variety of network architectures. So we want to obtain the Ridgelet transform for a deep convolution network or a deep fully connected network, right? But until very recently, the Ridgelet transform is known only for depth to fully connected network. And these two professors, Murata sensei and Candes, those two professors are the first to find the Ridgelet transform for depth 2 case. And Murata sensei is my supervisor of my PhD. So I asked him how to find the Ridgelet transform, but he said he just forgot. So in the last few years, we developed a systematic method to obtain or derive the Ridgelet transform for general neural networks. And until today, we developed two methods, two schemes. One is by using the Fourier expression, and the other is by using the group representation theory. And the main topic today is that in the second half of this talk, I want to explain the scheme by using the group equivariant functions or group representation theory, because the Fourier expression method is also really a strong approach, and you can obtain a Ridgelet transform for neural network on manifold or group convolution neural network. But this method is limited to a single hidden layer case. But we want to analyze the deep neural network, and only by using the group representation theory. And very recently, we succeeded to obtain the Ridgelet transform for deep neural network. So in the second half, I will introduce the method by using group representation theory. Okay. So okay, I will skip these three slides. These are methods by Fourier expressions, and if I have time, I will explain this method. Okay. So let's move to the deep Ridgelet transform for joint equivariant machines. Okay. So I first introduce the feature map. This is a very general feature map. Let G be a group, and let X, Y, and Z be G sets. G sets means that those are just sets, and on those sets, group G acts. So those sets have a group G action on those sets. And suppose that I call this phi to be a feature map. Feature map means that this is a function from X to Y parameterized by Z. And we call a feature map phi is joint G equivariant when it satisfies the following condition. This condition means that if group G acts on data and the parameters simultaneously, then the output will be acted by group G. This is the joint action. So, and traditionally, there is a group equivariant networks, right? Like the networks proposed by Taco Cohen, for example. And those networks are a subclass of our joint group equivariance. So, and the difference is that in the traditional group equivariance case, we do not assume the group action on parameter Z. So by carefully designing the network structure or parameter of network, the group equivariant network is designed so that if we rotate the input X, then the feature will be rotated, right? And the parameter is fixed. But in our case, we also allow the group action on parameters. So the traditional case corresponds to the group action on the parameter is trivial, right? I mean, g dot gz equal gz, so no action. No action corresponds to the classical group equivariant feature map. And why we consider this joint action is that the main reason is that the fully connected network, the main topic, main focus today is covered in this joint setup. But it, of course, excluded from this classical group equivariant setup. Right. So this is a main motivation to consider a joint group equivariant feature map. And in addition, obtaining joint equivariant maps is very easy. Suppose you have an arbitrary mapping from x and y, from x to y without any parameter, then act group G in this manner. So this group action is sometimes called the regular action of group G on the function on x to y. So this is a regular action. And regard this element, group element G itself as a parameter. Then the obtained function phi of x times G to y is joint equivariant. That's somewhat a canonical way to obtain a joint equivariant map. So in this case, the group G itself will be a parameter. And another nice thing is that suppose we have n joint equivariant maps, then the composition of those n equivariant maps again joint equivariant. This property is nice to analyze a deep neural network or deep concatenation of feature maps, because the main focus of this study is to analyze the deep structure. So that's a nice property. And using the group joint equivariant features, we introduce a joint equivariant machine. Okay, suppose let G be a locally compact group. So this assumption sounds technical, but this is due to consider the integration on the group G. And suppose X, the input space X, and the parameter space Z are G spaces with invariant measures dx and dz. And suppose the output space Y to be a separable Hilbert space with unitary G action. Here I assume Y to be a Hilbert space mainly because we want to consider integration of feature maps. So this is essentially the extension of a continuous neural network. So we define a joint equivariant machine as an integration of feature map with respect to Gz. So in the end, this will be a function of x with weighting function gamma and feature phi. And we do not use this property, but this joint equivariant machine is again a joint equivariant. Okay, so in this sense, a joint equivariance is ubiquitous, much ubiquitous than classical group equivariant feature map. Okay, and this is a main result. The first column corresponds to the recap. This is a definition of a joint equivariant machine. And we want to find the inverse transform for this gamma, right? And this is the gamma. This is a Ridgelet transform. So let psi be another joint G equivariant map, feature map. And suppose F be an arbitrary mapping from X to Y. then the Ridgelet transform is given by a scalar product or similarity between fx, the function f to be approximated by machine, and the feature map psi. This is the definition of Ridgelet transform. And this first item is the only assumption we need to verify. As long as this assumption holds, we can say that this Ridgelet transform is an inverse transform for the joint equivariant machine. This is the main result. And what is this assumption? This assumption sounds a bit technical. Is that let pi be a regular action of group G on the L to X to Y. L to X to Y means that this is a square integrable vector valued function on X or Y valued function on X. And the construction of representation pi is somewhat a regular one. I mean, the regular representation of group G on L2 space. And the assumption is that this pi is irreducible. The irreducibility, verifying irreducibility of regular representation is sometimes difficult, but they have a long history, so you can find many examples of irreducible regular representations. So as long as this pi is irreducible, if we substitute the Ridgelet transform to the place of unknown function gamma, unknown weighting function gamma of a joint equivariant machine, then the equivariant machine reproduces the original function f up to the constant c, depending on feature maps phi and psi. That's the main result. And nice thing is that the proof is very short. But if I have time, I will explain this proof. But we essentially use the Schur's lemma. Schur's lemma is essentially a rephrasing of irreducibility of unitary representation, and yes, we use Schur's lemma. And in order to use Schur's lemma, we use the assumptions of the joint equivariance of feature maps and the group equivariance of measures dx and dz. Okay. And we have 3 examples. The first example is depth to fully connected network case. So this case is already known in the 1990s, but we can reprove this Ridgelet transform from the perspective of group representation theory. In this case, the group G is the affine map. Affine map is a semi-direct product of regular matrices GL, M, and the translation RM. And the group action on data domain RM is the typical one, an ordinary one. I mean, the G.X is given by the L times X plus T. Here, L corresponds to the matrix from GL, and T corresponds to an arbitrary vector in RM. On the other hand, we can also find the dual G action on parameter domain of affine group. This looks really weird, tricky, but this is made so that the simultaneous action of group G on X and AB left the feature map. We leave the feature map invariant. I mean, if we act group G on X and G on AB simultaneously, then X will be translated to Lx plus T. On the other hand, A and B are translated to L inverse transpose A, and B will be transported to B plus, blah, blah stuff. So everything looks really weird, but in the end, all the group actions will be cancelled, and A dot X minus B is reproduced. And this is a trick. So, and this is a meaning of a dual group action on parameter domain. So now we saw that this feature map sigma A dot X minus B is joint group invariant under the group action of Affine group. According to the general result, if we put the integration of sigma A dot X minus B with respect to parameter as neural network, and rho A dot X minus B with respect to data X as a Ridgelet transform, then this R works as an inverse transform for neural network operator. And here is an important lemma. This is a known result that the unitary representation defined by of affine group defined by a regular group action on function f is irreducible. So the infinite representation of affine group on L2 space is known to be irreducible. This is a known fact. So according to a general result, Nn of R reproduces the original function. Okay, that's the first example. And the second example is for depth n case. For depth n case, the group G is a product group of orthogonal group OM and affine group. And again, the group action on data is given by an ordinary group action of affine group on X. Here L is a matrix and T is a vector. On the other hand, we can find several dual G action, but this is one example. One example is that group action on parameter is only for the first layer parameters and output layer parameters. And the group action looks like, again, a technical one, but if we, under this group action, we can verify that the deep feature map defined by the composition of n times composition of this feature map is joint equivariant. We can verify easily. In addition, the unitary representation pi g defined by a regular group action on vector valued function f is irreducible. This is not known, but we proved the irreducibility of this group action. So according to general result, if we substitute the Ridgelet transform given by defined by this integral transform to the place of unknown function gamma, then it reproduces the original function f. So this is the Ridgelet transform of for the deep neural network. But meaning is somewhat easy. I mean, this is essentially measures the similarity between vector valued function f and the feature map psi. So this is somewhat, the interpretation is somewhat easy. Okay, and finally, the final example is the one unknown to have the universality. So again, the group G is an affine map, and the group action on data is an ordinary group action of affine group on RM. On the other hand, we consider the feature map of this form. This form is some slight modification of a fully connected network. I mean, X transpose B plus C. This part corresponds to an ordinary fully connected network. And in addition, it has a second order term or a quadratic term, right? So this feature map is understood as a quadratic form followed by a nonlinear activation function. And as far as we know, we notice there is no such kind of a network there has been no such kind of a network proposed. So of course the universality of this network is not known, but under this dual group action, like this, we can verify that this feature map is again a joint equivariant. And in addition, as we already see that the regular action of affine group on L2 functions is irreducible. So according to a general result, this quadratic form neural network is L2 universal. This is an unknown result. Okay, to wrap up, the ultimate goal of this study is to characterize the deep learning solutions. And yes, the Ridgelet transform is a right inverse operator S of R of satisfying the S of R of F equal the original function F. And the Ridgelet transform can explain how network parameters are assigned or distributed after the learning process. But it was not known until very recently. It was not known for deep neural network or modern convolution neural networks. And we developed two schemes. One is by using the Fourier expression, and the other is by using a group representation theory to obtain the Ridgelet transform. And in this talk, I explained the second approach. Okay, this is the end of my talk. Thank you very much.
Okay, thank you. Yeah, do we have questions from audience? Okay, let me first ask one. So in the first part, for neural network to express a function, there are multiple ways, right? Even by this density integrated form. So how can you find this inverse operator if the solution is not unique?
Oh yeah. Maybe you mean this, right?
Yeah, that's right.
Yeah,
This one.
Yeah. I didn't mention it, but I assumed
Oh yeah.
yeah, L2 regularization, then the solution will be we can establish a uniqueness of a solution.
Okay. So if I change this regularization term, this distribution should be changed, right?
Exactly. We will obtain a different distribution.
Oh yeah. So for example, this for this specific regularization, what's the meaning, or do you have any specific interpretation for this distribution?
I think because this is a ridge regularization or L2 regularization, this is somewhat a classical regularization.
Yeah, the solution has some very specific neurons in the same direction always. Actually, during our training of like neural networks, we found that if you use very small initialization, the neurons A and B, they will be in a similar direction or aligned together.
Yeah.
But here you don't have any training, right? You just add a regularization and you get this distribution.
Yeah, right.
Yeah.
In this setup, we this part corresponds to the initial distribution. We simply
Yeah,
use
that's right.
a uniform distribution, and then after the gradient descent, these dots gradually move towards blue part or red part.
Yeah.
So yeah, this is more like a active regime, and this is somewhat different from a lazy regime. Mm. Mm.
Okay. So what's the meaning of this L square in the right down corner of this regularization term? Yeah, this L square is L2 no? Of this
Yeah, this
C?
is essentially L2 norm. Yeah,
Okay.
yeah, that's
Okay.
right. Mm. Mm. So in a sense,
Thanks.
this is a really classical result.
Oh, yeah.
Uh,
Okay.
Maybe, for example, for L1 or lazy regime, we can find a different rigid transform corresponding to the regularization term.
Okay.
Mm.
Thanks. Do we have more questions from the audience? We don't have too many audience, so if you have question, you can just unmute yourself.
Mm-mm.
Yeah, even though maybe we can stop here, Professor Xiu.
Yeah, thank you very much.
Okay, thank you very much for sharing this very interesting talk.
Thank you
Okay,
for the invitation.
okay. See you.
See you.
Yeah,
Say
bye
hello
bye.
to Chang Shao.
Okay, sure. Okay, bye bye.
Okay, bye bye.